are on this example. Oh yeah, that's right. That's right that you mentioned that you had. Okay, so we have this beam with this force at the end, and at the midpoint, (4,000 newtons and 2,000 Newton meters. Don't make me shoot you, Scott.
Are you licensed to carry yet?
What?
Are you licensed to carry yet?
No, not yet. It's in the mail, my license. And we're going to analyze that line there. And the cross section is a hollow rectangle. There's the neutral axis. The thickness the whole way around is 0.003 meters. So 3 millimeters. The height is 5 centimeters. And the width is 2 centimeters. And we're trying to calculate the stresses. So let's calculate the stresses over here, where we're halfway between the neutral axis and the top. So I didn't make a distinction before, but there is a distinction that we need to make between what's happening here and what's happening here, and that is because of which elements we're dealing with due to torsion. And why did we choose a hollow rectangular cross section? That's true. Why did I choose it? That's the only shape, the only cross-sectional shape where we can have every kind of internal load acting and calculate the stress anywhere along the cross section. We can also do some calculations for a circular shape, but we can only do it along the neutral axis. So this is the only one where we can move away from the neutral axis. And then we can do other shapes if some of those internal loads are zero, depending on what all the restrictions are. And we're going to ignore the weight because the weight is 26 newtons compared to 4,000 newtons, 5,000 newtons. All right, so first thing you have to do is make the cut and calculate the internal loads at that red line. So we have the downward force of 4,000, torque of 2,000, the horizontal force of 5,000, and then the internal loads, tension, shear force, bending moment, and torque. Newton's second law says 5,000, 0. plus 0, negative 4,000 plus T, negative V is equal to zeros. So we have a tension of negative 5,000, shear force of negative 4,000. So is this in tension or compression? Yep, compression because tension's negative. And then the moment equation about the x-axis. We have negative 2,000 plus fancy t is equal to 0. So the internal torque is positive 2,000 Newton meters. And then the moment equation about the z-axis. Okay, what produces moments? We'll do this as the about point. The 4,000 Newton force, what's its moment arm? 0.5. So we got 0.5 times 4,000, and then is that clockwise or counterclockwise? Clockwise, so negative. And then we got plus m minus v times the moment arm for v is 0.75. That's equal to 0. So negative 2,000, these. So we got m is equal to positive 2,000 minus 3,000, so negative 1,000. And that's Newton meters. How'd I get what? Because we're not, instead of calculating these as a function of x, we know that we're just analyzing it at this location. And so, and that location, well, I didn't write anything to say that, but I said before it's halfway between the middle and the end. So we just happen to know that this distance is 0.75. If you wanted to calculate this stuff as a function of x, then you'd have to calculate these sub-functions like we did in internal loads. But the red line is where we're calculating the stress, yeah. So now we're going to just go one by one. We know that the total stress is the stress due to tension plus the stress due to bending moment plus the stress due to shear force plus the stress due to torque. So I'll start with the stress due to tension. We have a tension of negative 5,000. Sigma XX, and this is for a coordinate system like this, X, Y, and then Z coming towards us. So sigma XX is equal to the internal tension divided by the cross-sectional area. I feel like we calculated that before, did we? .84 times 10 to the minus fourth. We haven't done this whole calculation, have we? Okay. Just, I can just picture everyone's just like, didn't we already do this? Just let him talk. It's not even worth it. Yeah. Oh, okay. Right. That's right. That's right. So sigma xx is equal to negative 5,000 divided by 3.84 times 10 to the minus 4. So what do you get for that? Times 10 to the 7. And it's like 1.30. Okay. Let's keep a bunch because, okay, so let's say 1.302 negative times 10 to the 7th pascals. And so the stress tensor due to internal tension is negative 1.302 times 10 to the 7, and then zeros. And now the stress tensor due to the bending moment. We know sigma xx is equal to negative my over I. So let's first calculate that area moment of inertia. That's 1/12 times, so the way we're going to do this is we're going to calculate the area moment of inertia for the solid outer rectangle. Then we're going to subtract the area moment of inertia for the solid removed rectangle. So we have 1/12 times the base of the outer rectangle is 0.02, and the height of the outer rectangle is 0.05, and that's cubed. And then we're going to subtract 1/12 times the base of 0.14, 0.14, yeah, 0.14, and then times 0.044 cubed. Let's calculate that. Okay, and that's meters to the fourth. So let's see, the bending moment is negative 1,000. So sigma xx due to bending is equal to negative 1,000 times y. What's y for the point in the cross section that we care about? Yes. So this is, so it's 0.025 from here to there, and it's half of that. So 0.0125. That's always easy to make mistakes with. I usually give the dimensions as the heights, but those y values aren't going all the way up the height. They're going from the center to the top or the center to the bottom. Okay, so, and we're going above the neutral axis, so it's positive. If you're going below, you have to use negative. So 0.0125. And then divided by 1.0895 times 10 to the minus 7. And what do you get for that? For the eighth? Okay, pascals. Okay, so before we go on to shear force and torque, So we've done all the things that in this coordinate system affect the x normal stress. If we're just looking at the normal stress in this coordinate system, would we have a bigger absolute value for a point like what we're looking at, or for a point below the neutral axis? And how do you know? It's actually below. That's a good guess, you know. Got 50% chance. Might as well take it. Because when you add these two together, so the stress due to bending moment is always going to be positive on one side of the neutral axis and negative on the other side. Okay, and so, but the stress, the XX normal stress due to tension is always going to be the same no matter where you are on the cross section. So above the neutral axis or below the neutral axis, one of those is going to have the stress due to tension and the stress due to bending offset, and one's going to have those two add. Okay, so in this case, the stress due to tension was negative. Above the neutral axis, the stress due to bending is positive. Below, the stress due to bending is negative. And so below, you get a bigger absolute value because you get, you know, this absolute value plus that absolute value. Although, you know, this is a case where there's a huge difference between the stress that comes from the bending moment. You know, it's much bigger absolute value than the stress that comes from tension, so it doesn't matter as much as sometimes. But when you're trying to figure out where you're most concerned about a material breaking, that's the kind of thing that you need to think about. You know, like, am I more concerned about above or below the neutral axis? And a lot of times that's the reasoning that goes into it, you know. Okay, now stress due to shear force. So the stress due to shear force in the rotated coordinate system, capital XY, is equal to negative VQ over IB. So let's first figure out what that Q is. So Q is the area above the line of interest times the distance from the neutral axis to the centroid of that area. And that calculation is kind of a pain here because we have to calculate the area and the centroid of, you know, a shape like this. So let's see, let's break it up into these three rectangles. So this distance is 0.0125. All of these thicknesses are 0.003. That's a good idea. That's easier. Yeah, it is better. Yeah, let's do it that way. Okay, so we'll think of it as an outer rectangle that has a height of 0.0125 and a width of 0.02. And then we'll subtract a rectangle with a height of 0.0095. I think that's right. And a width of 0.014. I'll call this 1 and this 2. So the area is equal to 0.02 times 0.0125 minus 0.0095 times 0.014. Can someone calculate that?
No.
Someone can.
No.
Oh.
May someone calculate that? I had a teacher who always did that. They're like
1.17 times 10 to the minus 4.
Mm-hmm.
That's a good point. That's the area. And now the centroid. We only care about the y-centroid. And that's 1 over the total area times the centroid of this one, of rectangle 1, which is 0.00625, times the area of this one, so times 0.02 times 0.0125. Minus the centroid of rectangle 2, which is 0.00425, 0.00475. Times the area of this, so times 0.0095 times 0.014. And what do you get for the centroid? Oh, that's what you get for the whole Q? Oh, okay. Yeah, I mean, if it works, it has to be something less than 0.0. 0.00795. 955. Okay, so does that make sense?
Yep.
Yeah, right. That makes sense. Yes. Okay, so Q now is equal to, this is equal to the distance from the neutral axis to the centroid of our area. So Q is equal to A times D, which is 1.17 times 10 to the minus fourth times 0.007955. Again, just expressing our total contempt for the rules of significant figures. And can someone calculate that? Times 10 to the minus 7. Okay. And this is meters to the third. Okay, so what do we know about Q? V, I mean. V is equal to negative 4,000. So tau I also did this thing with, this isn't the one where we do the rotated coordinate systems. So this is always just going to be the real x, y. So tau xy is equal to negative of negative 4,000 times 9.3075 times 10 to the minus 7 divided by I for the cross section. We had that before. 1.0895 times 10 to the minus 7. And then times B. So what's B for this cross section? That's, yeah, but you can think of that as like the total length of material that that we have resisting this shear. So that has to be a material base. So we're not going the whole way across the rectangle. Yeah, it's just 0.006. It's just this distance plus this distance. Yep, that's right. That's right. Yep. Because what it's asking is basically how much material do you have to resist that shear? And even though we want to calculate the value there, all of this is contributing to resisting that shear stress.
So only do 0.003 plus 0.003.
Right. Yep.
And then our point of interest was
Yes, that's right. Exactly. Yep. Yep, exactly. So 0.006. And can someone calculate that? $5.897. 5.697 times 10 to what? Times 10 to the 6 pascals. So, okay. So the stress tensor due to the shear force is 0. 5.697 times 10 to the 6, 0. 5.697 times 10 to the 6, 0, 0, and zeros. And then the last one is the stress due to the torque. This is a thin-walled tube. It's not circular. So we're going to use the equation that says tau, capital X, capital Y. This is the one where, in general, you have to rotate your answer, re-express it in a new coordinate system. Just because of the point I picked, we're not going to have to do that. But tau xy is equal to negative torque divided by 2 times the thickness times the area of that median. In this case, it does because we always choose a coordinate system. So our capital coordinate system always has the x-axis pointing straight out of the surface. In this case, the z-axis, not the x-axis. So this is our, capital Z because of the point I chose. But that also is the real z-axis, so we don't have to do any rotation in this case. So that's good news. Okay, so what do we have to calculate? We have to calculate, we have the thickness, we need to calculate that median area. So there's the median. And we want this area. The length this way is 0.017, and the height is 0.047. So the area is just those multiplied together. Do you have it? 7.99 times 10 to the minus fourth. There's a pretty thin wall on this, so look at the difference between that and the outer area and the inner area. Well, I guess we didn't take those intermediate ones, but if you calculate those, they're all pretty much the same thing. You wouldn't be introducing a lot of error into this by using the full outer area or the full inner area, and that's generally the case with these thin tubes. All right, and so tau xy is equal to the negative torque. Torque is 2,000. So negative 2,000. Oh, we still have to do the pole. Oh, no, that's for the other one. So divided by 2 times the thickness of the wall at the point that we are looking at. So that's 0.003 times that median area, 7.99 times 10 to the minus 4. And what do you get for that? Times 10 to the 8th pascals. And in this case, because of the point on the cross section I chose, that's equal to just regular tau xy. And so the stress tensor due to the torque is 0, negative 4.172 times 10 to the 8, 0, negative 4.172 times 10 to the 8, all the rest are zeros. So now the total stress is the one due to tension. So negative 1.302 times 10 to the 7, 0, 0, 0, 0. Right, that's the one for tension. Plus the stress due to bending moment. So 1.147 times 10 to the 8, 0, 0, all the rest zeros. That's sigma m. Plus the stress due to the shear force, 5.697 times 10 to the 6th. So 0, 5.697 times 10 to the 6, 0, symmetry, zeros. That's the stress due to shear force. And then the last one is the stress due to torque, negative 4.172 times 10 to the 8. 4.172 times 10 to the 8, that's in the XY spot. Symmetry, that's sigma torque. Okay, so what do we have? Basically, positive 1.01 so 1.01 times 10 to the 8th, right? And then for the XY stress, what do we get for that one? 4.11 times 10 to the 8th, 0, negative 4.11 times 10 to the 8th, 0, 0, 0, 0, 0. And then normally what you would want to know is you want to know the principal stresses, then use those principal stresses to calculate the max shear stress. I don't think that even steel
Oh, you would.
Oh, I mean,
I don't think that I don't know what the stress is that gets you out of the linear elastic range. There's a few ways to use these values to calculate it and whatever. Steel isn't, and most metals aren't brittle enough for the maximum shear stress to really be a very good predictor of when something's going to break. But you can use these stress values and the strain values in a few different ways to get guesses at when it's going to break. But I don't think steel can withstand that much stress.
Isn't the geometry also?
No, not really. We already took the geometry into account when we did all that stuff to turn it into stresses. That's sort of what's cool about stresses and strains is like you boil it all down to a handful of numbers that just tell you, you know, yeah. Mm-hmm. Any questions about that? Okay, so on a test, I won't ask you any questions longer than that one.
That's good.
Except I suppose I could put it in a different part where you have to do the rotation matrix. I can do that. Right, exactly. Exactly. And then the principal stresses and whatnot. Oh, and also I could make you solve a structure to get into the yeah.
Develop a function that solves this.
Yeah.
Is what I'm hearing. Because if we can develop a function that works for these, we understand how it works, right?
Yes, that's right. Do it. So yeah, if I can maybe give you something like this with a distributed load.
Oh, this will be on there.
Calculate the stress at some point that I specify in that. Perfect. All of deform in one question. Ooh, that's a good idea. Well, actually, now that we're done with this, we're going to start leading into doing calculations for statically indeterminate structures, which is kind of cool because, you know, like when you took statics, maybe you found it a little unsatisfying that it's like, okay, so you have a structure like this, you know. If you have a roller here, you have some loads. Everything's good. You can calculate all those external loads on all the bodies. But you just change it so that this is another pin joint. Using statics, there's no way to calculate what those external loads are. But that's not satisfying because I mean, people build stuff like that all the time that's statically indeterminate. Nothing weird happens. It doesn't open up a wormhole or anything, you know. So there must be a way to calculate, and your intuition tells you it's not like it's toggling between some pair of internal loads or whatever. So there must be some way to calculate it, and it turns out there is, but you have what you need to do in order to calculate it is you need to take into account how the individual members deform as they're loaded. And so if you know the material and you know its material properties through Young's modulus and Poisson's ratio, you can put additional requirements in that are enough for you to calculate how those loads are distributed in a statically indeterminate system. It's kind of interesting. So the next thing we're going to talk about is macroscopic deformations. So if you put these loads on this thing, does this get 3 millimeters longer? Does it dip down 2 millimeters? Or what's the overall deformation along the whole thing? And then we'll use that idea to do statically indeterminate systems. So yeah, that's true. So that's the absolute longest I could make a problem is give you a statically indeterminate structure, have you calculate the loads on that, calculate the internal loads once you've calculated the external loads, and then do the stresses, including the rotation matrix. That's all.
For now.
Yeah, that's all. I can't do any more. That's true.